On objective 3, we have that we want to decompose P over Q, where Q has a non-repeated, irreducible quadratic factor. So with case 3, Q contains a non-repeated, irreducible quadratic factor. We suppose that Q contains a non-repeated, irreducible quadratic factor of the form ax squared plus bx plus c. Then in the partial fraction decomposition of P over Q, we allow for the term ax plus b over a times x squared plus bx plus c, where the numbers capital A and B are to be determined. So remember our irreducible ax squared plus bx plus c, that would be if you tried to use the quadratic formula and you could not because b squared minus 4ac was negative. So for example 3, let's go ahead and find the partial fraction decomposition of 3x minus 5 divided by x to the power of 3 minus 1. So just as before, the first thing we want to do is check to see if the denominator can be factored. So I keep wanting to call that a. X to the power of 3 minus 1 can actually be factored. So we factor it. X to the power of 3 minus 1 can be factored into x minus 1 times x squared plus x plus 1. So it can be factored in this sense. This is just using properties of x to the powers of 3's plus or minus another value to the power of 3. So 1 to the power of 3 is still just 1. So x to the power of 3 minus 1 can be factored using that identity. Since we had this, it would factor into the form x minus 1 times x squared plus x plus 1. So that's an identity that would have been learned in Math 95. So, all right. So we can factor x to the power of 3 minus 1 into x minus 1 times x squared plus x plus 1. So we factored our denominator into two separate terms. So we can say that this gives us a non-repeated linear factor, which is x minus 1, and an irreducible, a non-repeated irreducible factor, a non-repeated irreducible quadratic factor, x squared plus x plus 1. So this tells us that we have two factors that are being multiplied together. They are not the same, so therefore we use case 1 to identify basically the first factor, which is x minus 1. So we say by case 1, we get that a divided by x minus 1 as a partial fraction. Then by case 2, we identify our second term, which is our non-repeated irreducible quadratic factor. So that means we use case 3. Ooh, 3, I wrote case 2. By case 3, we get, and this turns into b times x plus c divided by x squared plus x plus 1 is another partial fraction. So this means our partial fraction decomposition did not spell that right. Decomposition will look like 3x minus 5 over x to the power of 3 minus 1 is going to end up being a over x minus 1 plus bx plus c divided by x squared plus x plus 1. And now we can multiply each term by x over 3 minus 1. Or we can just say x minus 1 times x squared plus x plus 1, which we know is equal to x to the power of 3 minus 1. In order to get three x minus 5 is equal to a times x squared plus x plus 1 plus bx plus c times x minus 1. So we want to expand this as much as possible. We want our terms to now be separated with terms of x squared, x's, and then constants. So we still have 3x plus 5, and we can distribute our a. So now we get a times x squared plus ax plus a. Plus, now we want to multiply bx plus c times x minus 1. This gives us bx squared minus bx plus cx minus c. Now we can go ahead and regroup them in the terms that they are in. So we have a plus b times x squared plus a minus b plus c times x. And then lastly, we have plus a minus c. So now we've grouped them with their coordinating degrees of x. Now, we can try to let x be equal to certain values, but what we see is that even if we were to let x be equal to 0, which would cancel out quite a few terms, it would still leave us with an a minus c is equal to -5. It doesn't really give us a definitive value. We would still be replacing a lot of other terms to try and solve for specific terms. So in a case like this, it is easier to do the identity that we did from example 1. So in this case, we will set up our identity. So this leads us to an identity of, and in this case, 3x minus 5. Or, in other words, a system of equations. But basically, this is going to give us that a plus b, which is being multiplied, by x squared is going to be equal to 0. Because there is no x squared term in 3x minus 5. That means that a plus b has to be equal to 0. Then a minus b plus c times x, this has to be equal to 3. Then lastly, a minus c has to be equal to negative 5. We can see that this is because a plus b times x squared has to be equal to 0x squared. This is because a minus b plus c times x has to be equal to 3x. And this is because a minus c times nothing, just the constants, they have to be equal to negative 5. So solving for these equations, which in this case we'll call this equation 1, equation 2, and equation 3. So from equation 1, a plus b is equal to 0, so we get a is going to end up equaling negative b. So we're going to use this in our other equations. So using this in equation 2, we get that a minus b plus c is equal to 3. A is equal to negative b. So this gives us negative b minus b plus c is equal to 3, which gives us c is going to be equal to 2b plus 3. So now we have an equation for c. Then we can use this in equation 3. So for equation 3, we're going to replace a and c so that they're both in terms of b. We get that a is negative b minus c, which is 2b plus 3, is equal to negative 5. Simplifying this gives us negative 3b minus 3 is equal to negative 5, which this turns into negative 3b is equal to negative 2. Dividing each side by 3, this gives us that b is equal to 2/3. All right, so we have a value of one of our terms, which means we can find the value of our other terms. So b is equal to 2/3. We know that a is just negative b. So since b is equal to 2/3, a is equal to negative 2/3. Then we can actually solve for c. So we get that then c is equal to 2 times 2/3 plus 3. 2 times 2/3 is just going to end up being 4/3 plus, in terms of 3, this will be 9/3, which is equal to 13/3. And thus, we have our values of a, b, and c. And we are going to put this right into our partial fraction decomposition. We do not really have to worry that much about making sure that we don't have fractions within fractions. We can place them right in, because especially with b and c, they're going to become their own equation. It's going to be a mess. So we can just go ahead and say then our partial fraction decomposition is 3x minus 5 divided by x cubed minus 1 is equal to negative 2/3 divided by x minus 1 plus 2/3 x plus 13/3 divided by x squared plus x plus 1. If having fractions within fractions ends up bothering you a lot, you can also factor that out. So you can say, or it's 3x minus 5 divided by x cubed minus 1 is equal to negative 2 over 3 times x minus 1 plus also 2x plus 13 over 3 times x squared plus x plus 1. You can also write it out like that if you would like. We'll put this in blue. The one we have in yellow is technically in the form that it asked for, so writing in this form would be acceptable as well. But if for whatever reason in my math lab it requests that you don't have fractions within fractions, you could write it this way as well. So, all right, our last objective here, objective 4, we want to decompose P over Q, where Q has a repeated irreducible quadratic factor. Case 4, we suppose the polynomial Q contains a repeated irreducible quadratic factor, ax squared plus bx plus c to the power of n, where n is greater than or equal to 2, for n is an integer and b squared minus 4ac is less than 0. So once again, just establishing this idea that it's going to be irreducible. Then in the partial fraction decomposition of P divided by Q, we allow for the terms a sub 1 times x plus b sub 1 divided by ax squared plus bx plus c plus a sub 2x plus b sub 2 divided by a times x squared plus bx plus c to the power of 2. And you go all the way up to the highest power, which would then be looked at by a sub n times x plus b sub n divided by a times x squared plus b times x plus c to the power of n. Whew. Where the numbers a sub 1, b sub 1, a sub 2, b sub 2, all the way up to a sub n, b sub n are to be determined. All right. So example 4, we want to find the partial fraction decomposition of x to the power of 3 plus x to the power of 2 divided by x squared plus 4 to the power of 2. So x squared plus 4 is irreducible. It's fairly easy to see right off the bat that it is going to be irreducible, and we have that it is repeating. So we don't really need to check our denominator to see if we can factor. That essentially was our check, saying x squared plus 4 is irreducible. It's the same thing being multiplied twice, so we're using a repeated irreducible quadratic factor. So we can write that out. We are using a repeated irreducible quadratic factor so x squared plus 4, sorry, the factor is x squared plus 4 squared. So we use case 4 to get that x cubed plus x squared divided by x squared plus 4 squared is going to then be equal to ax plus b divided by x squared plus 4 plus cx plus d divided by x squared plus 4 squared. So all right, now we have what our partial fraction decomposition is going to end up looking like. So we want to multiply each term by x squared plus 4 squared to clear our fractions and get that x cubed plus x squared is equal to ax plus b times x squared plus 4, put those in parentheses, plus cx plus d. Now remember, we want to collect our like terms and expand these functions. Oof, couldn't remember the word there. So by expanding this gives us ax to the power of 3 plus 4ax plus bx squared plus 4b plus cx plus d. And now we'll collect our terms. When we collect our terms, we're still left with ax to the power of 3 and bx squared. But now we also have 4a plus c times x and 4b plus d. So we've collected our terms. This is also going to be another case where it's easiest to use an identity. And it's easiest to use an identity because quite a few of these terms are just going to be set equal to 0. So we can say this gives us our results as a system of equations. So, there you go. Using our system of equations, this means that a has to be equal to 1. A has to be equal to 1 because it's the only x cubed term. We have 1x cubed. Then we also get that b has to be equal to 1 because there's only a 1x squared term. Then we have that 4a plus c has to be equal to 0. And 4b plus d has to be equal to 0. So we get this, since ax cubed has to be equal to 1x cubed, then same thing, since bx squared has to be equal to 1x squared. Then since 4a plus c times x has to be equal to 0x. And then since 4b plus d has to be equal to 0. All right, so right off the bat, we found what a and b are. And since we found what a and b are, we can just plug in our values of a and b to solve for c and d. So we'll just call this equation 1 and equation 2. So for equation 1, we plug in a is equal to 1 to get 4 times 1 plus c is equal to 0. We get 4 plus c is equal to 0, which means that c is equal to -4. Then for equation 2, we plug in b equal to 1. To get 4 times 1 plus d is equal to 0, which means that 4 plus d is equal to 0, which means that d is equal to -4. And thus, we found all of our values for A, B, C, and D. So we say thus, A is equal to 1, B is equal to 1, C is equal to -4, and D is equal to -4. This gives us our partial fraction decomposition where we originally had x to the power of 3 plus x squared divided by x squared plus 4 squared is just going to be equal to x plus 1 divided by x squared plus 4 plus -4x minus 4 divided by x squared plus 4 squared. And that wraps up our final example on our final section. So we're done with 11.5. That means that I will see you again in the final exam review.